Chapter 3. Overview of General Relativity. Let us now venture deeper into the cosmic tapestry with Einstein's general theory of relativity. Imagine the universe as a vast, serene fabric, gently bending and curving under the weight of stars and planets. Einstein extended his revolutionary ideas to encompass gravity, transforming our understanding of this fundamental force. Before Einstein, gravity was seen as a force acting at a distance, as described by Newton. But Einstein envisioned something more profound. Gravity is not a force, but a curvature of space-time caused by mass and energy. Space-time and gravity. Imagine space-time as an enormous flexible sheet, much like a trampoline. When you place a heavy object, such as a bowling ball, on this sheet, it creates a dent or a curve. Now, if you roll a marble near this indentation, the marble will naturally move towards the bowling ball. It might seem like the bowling ball is pulling the marble towards it, but in reality, the marble is simply following the curved path of the sheet. This is how Einstein explained gravity. Objects move along the curves in space-time created by other masses. Large objects like stars and planets create significant curves in space-time, and smaller objects move along these curves. Thus, what we perceive as the force of gravity is actually objects following the curved paths in the fabric of space-time. The bending of light. One of the remarkable predictions of general relativity is that light, despite having no mass, follows the curvature of space-time. Imagine shining a flashlight across a trampoline with a heavy object in the middle. The light beam would curve around the indentation, just as light bends around massive objects in space. This was spectacularly confirmed during a solar eclipse in 1919. British astronomer Sir Arthur Eddington observed starlight passing near the Sun and noticed that the light bent around the Sun, an effect that could only be explained by the curvature of space-time. This observation provided one of the first empirical confirmations of Einstein's theory and was a pivotal moment in the acceptance of general relativity. Black holes. General relativity also predicts the existence of black holes, regions of space where gravity is so intense that not even light can escape. Picture a star that has exhausted its nuclear fuel. Without the outward pressure from fusion to balance gravity, the star collapses under its own weight, compressing its mass into an incredibly small and dense point known as a singularity. The curvature of space-time around this singularity becomes so steep that nothing, not even light, can escape from this region, creating a hole in space-time. These mysterious objects are fascinating to both scientists and the public as they challenge our understanding of physics and offer a glimpse into the extremes of gravitational effects. The study of black holes continues to reveal new insights into the nature of the universe. The expanding universe. Einstein's equations also suggest that the universe is not static but expanding. Initially, Einstein himself doubted this implication and introduced a cosmological constant to keep the universe static. However, observations by astronomers like Edwin Hubble later confirmed that distant galaxies are moving away from us, indicating that the fabric of space-time itself is stretching. Imagine blowing up a balloon with small dots on its surface. As the balloon inflates, the dots move away from each other. Similarly, as the universe expands, galaxies move away from each other, revealing that the universe is dynamic and constantly changing. This discovery has profound implications for our understanding of the cosmos, suggesting that the universe had a beginning, a Big Bang, and has been expanding ever since. Practical implications. While these concepts might seem abstract, they have practical implications in our daily lives. For instance, GPS technology relies on general relativity to provide accurate positioning. The satellites orbiting Earth experience different gravitational forces and speeds compared to us on the surface. These differences cause time to pass slightly differently for the satellites than for clocks on Earth. By accounting for these relativistic effects, GPS systems can maintain precise accuracy, allowing us to navigate with pinpoint precision. General relativity also plays a crucial role in the field of astrophysics, helping scientists understand the behavior of celestial bodies, the formation of galaxies, and the evolution of the universe. Its applications extend to various technologies and scientific disciplines, making it one of the most important theories in modern physics. In the next chapter, we'll explore the historical context and the profound impact Einstein's theories have had on science and our understanding of the universe. We'll delve into the controversies, the pivotal moments, and the ways in which Einstein's work has transformed the scientific landscape, opening new frontiers and inspiring generations of physicists. So, relax and let your mind wander through the wonders of space-time and the revolutionary insights of general relativity.